In this lecture, we are going to talk about discrete random vector. Before going into the definition of discrete random vector, just recall what was the definition for discrete random variable. So, the definition of the discrete random variable was, it is nothing but x is discrete if and only if x is a discrete random variable if there exists and at most countable set D, which is a subset of R, at most countable set D, such that probability that x equals to x is strictly greater than 0 for all x belongs to D, and probability that x belongs to D is equals to 1. Okay, that was the definition. So basically, if I can find out a countable, at most countable set D, such that probability for each point in D is strictly greater than 0 and x belongs to D, that probability is exactly equals to 1, then we say that x is a discrete random variable. Now using the same thing, we can give the definition of the discrete random vector. The only change is this: in this case, we will have that instead of the D, which was support of the discrete random variable, which was a set in R, now I have a subset of R. So this will be subset. This sign will be subset. So I am sorry for this typo. So a random vector xy is said to be a discrete random variable. Discrete random vector are said to have a discrete distribution if there exists an at most countable set Sxy, which is a subset of R square, such that probability xy equals to small xy is strictly greater than 0 for all xy in Sxy, and probability that xy belongs to xy is exactly equals to 1. So in the previous case, in case of the discrete random variable, we have a subset of R. Now we have a at most countable subset of R square, and the rest of the definition are exactly same as before. Okay, so just like the previous case, in this case also Sxy is called the support of xy. Again, in the similar fashion, that when we define the discrete random variable, the probability mass function is defined as the function that probability x equals to small x. In the similar way, the joint probability mass function or joint PMF is defined by this function, where basically the function at the point xy takes the value probability x, the probability that x equals to x and y equals to y. Clearly, this probability will be 0 if I am outside the support, but when I am inside the support, this probability is strictly greater than 0. Okay? The same definition, only it is extended from the one dimension to the two dimension. Similarly, it can be extended for multi-dimension also, though I am not going into that proof that definition, but you can understand that this definition is a very straightforward one. Property of joint PMF. Again, it is a very similar one, that for the PMF, the two main properties was that PMF is always greater than equals to 0, and if I take the summation of the PMF over the support, it turns out to be 1. The similar thing is true here. In this case, the PMF is greater than equals to 0 for all point in R square, and the summation of the PMF is equals to 1. Okay, so these things are very straightforward extension of that of the one-dimensional random variable. So once you understand the one-dimensional random variables, the extension is very straightforward. Okay, next theorem says that the opposite is also true. Opposite of the previous theorem is also true. So if G is a function from R square to R, we satisfy the properties 1 and 2 above. 1 and 2 above, that basically mean that it satisfies these two conditions, that the gxy is greater than equals to 0 for all xy belongs to R square, and summation gxy equals to 1 over a at most countable set D of the subset of R square then this G function is a joint PMF of some two-dimensional random vector. So it's again similar to that of the previous one, that in case of the joint PMF or in case of the discrete random variable, we notice that if G is a function from R to R, satisfying two conditions. First is that it is always greater than equals to 0, and second is that if I take the summation over the set where it is strictly greater than 0, then it is 1, then these two conditions are satisfied, then that G function is a PMF of a discrete random variable. Exactly same thing is true here. Only thing is that now this function is a function from R squared to R, and then this set is a subset of R squared. Okay. Next one is a very important theorem. So, and it is a new theorem. What is this theorem about? This theorem basically tells that if I have a discrete random vector xy, then x and y both are discrete random variables. Not only that, I can find out the marginal PMF of x from the joint PMF of xy. Similarly, marginal PMF of y from the joint PMF of xy. So what the theorem basically says, okay, let xy be a discrete random vector with joint PMF fxy and joint support sxy, then x and y both are discrete random variables, and the joint PMF of x can be found by taking the summation of the joint PMF over all possible values of y. Note that in this case x is fixed. So for each fixed x is fixed, I need to take this sum. What is this sum? This sum is basically, as the x is fixed, I have to take the sum for all possible values of y such that x comma y belongs to the support of xy. Clear? Similarly, for y also I can able to find out that for y, for fixed small y, I need to take the sum over all possible points xy such that xy belongs to the support where y is fixed before. Okay? And if there is no point which belongs to this, then by convention we take that the value of the summation is 0. Okay? The proof is straightforward and it is given here. I am not going into the proof. I am leaving it for you. But take the main point that if I have a discrete random vector, each components are discrete random variables, and I can find out the marginal PMF from the joint PMF. Okay, right? So let us take some examples. So first example, I am given with a joint PMF, but there is a constant C. The first thing is that I need to find out the constant C, and then once I get the constant C, I will try to find out what is the joint PMF of X and what is the joint PMF of Y. Okay. So how can I find out C? So I can use the fact that first of all C has to be greater than equals to 0, right? Because joint PMF has to be greater than equals to 0, so C has to be greater than equals to 0. Not only that, if C is 0, then it will not be a joint PMF because sum will not be 1. There does not exist any countable set such that any at most countable set such that the sum is 1 if C is 0. So C has to be strictly greater than 0. Next point is that if I take the sum over the support is basically nothing but 1 2 up to n cross 1 2 up to n. Okay, set 1 2 up to n cross set 1 2 up to n, and if I take the sum over the support, then basically the sum has to be 1 if it has to be a joint PMF. So that condition we can use, and I can write the sum as summation x equals to 1 to n, summation y equals to 1 to n, the joint PMF and the support, the form of the joint PMF is C times y. You can plug in it here and then solve for C, and you can easily find out the C turns out to be this one. So that means the joint PMF of xy in this case given by this. Now once I have the joint PMF, I can find out what is the marginal PMF of x and marginal PMF of y. So how can I find out? Okay, notice that if x does not belong to this set, then there does not exist any xy pair for which the joint PMF is positive. That means if I go outside this particular set, then the marginal PMF of X has to be equals to 0. Okay? And now I try to find out what will be, if I go outside this set, the marginal PMF is 0. Now I need to find out this part when I am in the set, in this set, what will be the marginal PMF. So when I insert this set, then suppose I take X equals to 1. If I take X equals to 1, then what are the points in the support? The points are 1, 1, 1, 2, 1, 3, so on and so forth, finally 1 n, right? The pair 1, 1, the pair 1, 2, the pair 1, 3, the pair 1 n, all these n pairs are in the support. So I need to take the sum over this point, this n point. Clear? So that's what I did. For each fixed X in this set, the probability X equals to X can be written in this way, and which is basically nothing but X is fixed, and I take Y from 1 to n, and once I do this sum with C equals to this constant, I get it turns out to be 1 by n. So that's what's written here, and this distribution is sometimes called the discrete uniform distribution. Okay. Similarly, you will be able to find out what is the distribution of Y, and what is the PMF of Y. In that case, you have to take the summation over X, and the procedure is exactly as before. So I leave it for you. Let us take another example. In this case, you will notice that everything I have taken almost same as before. Only change is that now another restriction is given here, which is X is less than equals to Y. Clear? So when I take X is less than equals to Y, now the support changes. Okay? The previous example, the support was basically the cross product of these two sets. Okay? Cartesian product of these two sets. But now the support is different. The support is basically all pair xy belongs to R square, where X can take value 1 to n, Y can take value 1 to n, with the restriction that X is less than equals to Y. So it is not now in a square, but one triangle. It is basically nothing but the upper triangle of a square. Okay, upper triangle part of a square. Okay. So now if I try to find out the value of C, as before I have to equate the sum equals to 1, but in this case when I do the sum, I have to keep this restriction here. Okay? And when I keep the restriction, the range changes. Notice that in the previous case, the range was X equals to 1 to n, Y equals to 1 to n, but now range changes. X cannot go beyond Y. That's why the range from A for X is X equals to 1 to Y, and then Y can take value 1 to n. Once you do this sum, you will get that C turns out to be, when you solve for C, you will find that C turns out to be this one. So plug in this one and we get a PMF which is of this form. So you see that based on the support, our joint PMF completely changes. And it has to be, otherwise the sum will not be 1. Good? So once I have the joint PMF, I can try to find out what is the joint marginal PMF of X. Again, if X does not belong to this set, then there does not exist any pair XY such that any pair XY in the support. So that means the joint PMF is 0. So by default, basically our probability X equals to X has to be 0. Now if X belongs to this set, I can find out the probability X equals to X by taking this sum. Again notice that here I have to take the sum over Y, but Y cannot be less than 8. So the range of the Y here starts from X up to n. And once you do the sum, you will get this quantity. So that means the marginal PMF of X turns out to be this. Similarly, you can find out the marginal PMF of Y, and you can check this turns out to be this one. Notice that when you try to find out the marginal PMF of Y, you have to take the sum over X, and you have to be careful when you are writing the range of the X on the summation. Okay, clear? So I hope that these examples are okay. Cross check this example once again. And I stop here for this lecture. In the next lecture, we will see the continuous random vector. Thank you for listening.